All right, think about this for a second. Imagine glass that can shift almost instantly from perfectly clear to totally private.
Just like that, with a switch.
Yeah, exactly, like flipping a switch. Or picture a tiny, tiny wire sort of hidden inside a bridge.
Okay.
And it's silently measuring all the, the invisible stresses in the structure.
Wow, okay. Sounds a bit like science fiction, maybe.
Doesn't it?
Yeah.
But this is the real deal. It's the world of smart materials.
Exactly. And today, we're really diving deep into two incredibly innovative parts of this. The dynamic world of switchable glass, and then this pioneering use of vestibule glass-coated microwires for precision measurement.
Right. So our mission here is to unpack the science. How do these things actually work? We'll explore the benefits, which are pretty surprising sometimes.
Yeah.
Look at all the different ways they're being used,
Mm-hmm.
and really see how they're changing things from architecture to, like you said, structural engineering.
Yeah, get ready, because your whole understanding of, everyday objects might just expand quite a bit. Market impact, all that.
So we're connecting the dots between these two, sort of extracting the key takeaways for you.
That's the plan.
Okay, so with that set up, where should we start? Maybe with the smart glass. What exactly is it? And how's it changing our spaces?
Good starting point. So switchable glass or smart glass, privacy glass, people call it a few things. It's basically this revolutionary tech that lets glass change its transparency.
On demand.
On demand, yeah. And its light transmission properties, too. And what's interesting is how it changes. It responds to different stimuli. Could be light, could be heat, but most commonly it's an electrical signal.
Okay, you mentioned different stimuli. Does that mean there are different fundamental types of smart glass?
Broadly, yes. You can think of it in two main categories. First up is passive smart glass.
Passive, okay.
Meaning it uses natural stimuli, no direct electrical control needed from the user. So think of thermochromic glass. That's the kind that darkens with direct sunlight or heat.
Right, I think I've heard of that.
Yeah, but as of 2025, it's not really in active production. There were challenges with consistency, different climates. And the big one, no user control. You couldn't just decide you wanted it dark.
Oh, okay.
Then there's photochromic glass. Similar idea, but it changes transparency based on light intensity. You see it sometimes in cars, maybe sunroofs.
Like transition lenses for buildings.
Kind of, yeah. But again, the downside is that lack of direct on-demand control. It just reacts.
So the passive ones are interesting, but limited. That must mean the active versions are where the real action is.
That's exactly right. Active smart glass, this is the stuff that responds to an electrical stimulus. That's what gives you the on-demand control.
And this includes those acronyms you mentioned earlier, EC, SPD.
Yep. Electrochromic, EC, suspended particle devices, SPD, and Polymer Dispersed Liquid Crystal, PDLC. We'll get into the details of each.
Okay.
But the general idea, the core mechanism for all of them, is applying some kind of electrical voltage or current. This changes the molecular structure inside, or maybe aligns tiny particles within the glass layer.
Which then changes how light passes through.
Precisely. It alters the light transmission, letting it switch between being clear and being opaque, or somewhere in between for some types.
That ability to just switch, it seems like a huge advantage. I mean, beyond just the wow factor, what are the real benefits here? Why does this matter?
Oh, the benefits are significant. Number one is probably enhanced privacy, like instant privacy when you want it. Creates a really effective visual barrier.
Yeah, I can see that being huge in offices or homes.
Definitely. Then there's control of natural light and glare. You can regulate how much light comes in, which makes spaces more comfortable, can boost productivity, reduces annoying glare on screens.
And you mentioned energy efficiency earlier.
Right.
How does that work exactly? Is it a major saving?
It can be, yeah. By optimizing the natural daylight, you rely less on artificial lights. That's one part.
Okay.
And by controlling the amount of sunlight coming in, especially the heat component, you can reduce the load on your air conditioning. So, yeah, lower energy consumption, less heat gain. It all adds up.
Right. Makes sense.
Plus, there's a security aspect.
Mm-hmm.
In the opaque state, it can hide valuable things from view.
Good point.
And honestly, aesthetics and design freedom, it gives architects this sleek, modern tool. No need for bulky blinds or curtains sometimes. It just looks clean.
Yeah, it definitely has a futuristic vibe. So where are we actually seeing this stuff deployed now? Is it still mostly conceptual? Or is it out there?
Oh, it's definitely out there, and in really diverse places. In commercial buildings, you see it a lot. Offices, hotels, definitely conference rooms, partitions between spaces, even hotel bathrooms for that switchable privacy.
Ah, yeah, I can imagine that. What about homes?
Residential spaces, too. Windows, skylights are obvious ones, but also room dividers, shower enclosures, and people are integrating it into smart home systems.
So you can control your windows with your voice or phone.
Exactly. Voice control, app control, tying it into schedules or sunlight sensors.
That's pretty cool. And how easy is that smart home integration? Is it plug and play or more complex?
It's getting much easier. A lot of systems are designed now with integration in mind. Often it's just like adding another smart device controlled by a switch or through an app.
Okay. Are there other, maybe more specialized areas?
Absolutely. Healthcare is a big one. Hospitals, clinics, labs. Think patient rooms, operating rooms, instant privacy, but also huge for hygiene and infection control.
Because you don't need curtains or blinds that can harbor germs.
Precisely. Much easier to clean a glass surface.
Oh.
And then there's transportation. Cars, buses, airplanes, windows, sunroofs, sometimes even windshields or visors. Great for privacy and cutting glare without blocking the view entirely.
Okay, that gives a great overview. Now let's dive into those active technologies you mentioned. PDLC, SPD, and Electrochromic. You said PDLC, Polymer Dispersed Liquid Crystal, is the market leader. Why is that?
Yeah, PDLC really dominates something like over 95% of the modern privacy glass market. The key thing is it provides that instant, clear or opaque switch.
How does it work? What's inside?
So you've got these microscopic liquid crystal droplets, and they're just suspended, dispersed in a polymer matrix like a film sandwiched between glass.
Okay.
In the default state, no electricity. Those little crystals are all randomly jumbled up. They scatter light that tries to pass through, making the glass look opaque or frosted.
Right, so that's the privacy mode.
Exactly. Then you apply an AC voltage across it. The electric field makes all those tiny crystals snap into alignment.
Like little soldiers lining up.
Sort of, yeah. They line up, and their refractive index matches the polymer around them, so light can just pass straight through. The glass becomes transparent.
And you said it's fast.
Extremely fast. We're talking milliseconds. So you get really quick, precise privacy control. Flip a switch, boom, it's private. Flip it back, boom, it's clear.
What about power? Does it constantly need electricity?
It needs continuous AC power to stay clear. Usually around 3 to 6 watts per square meter, so not a huge amount, but it's constant when clear.
But when the power's off?
It automatically reverts to the opaque private state.
Right.
Which is actually a benefit. It's fail-safe for privacy and energy efficient if you only need privacy occasionally.
Okay. And the clarity. Is it perfectly clear when on and totally private when off?
Very high level of privacy. When opaque, you really can't see through it. And when it's on or clear, modern PDLC has excellent clarity, generally no noticeable haze. It's a binary function, clear or opaque, not really dimmable.
Sounds robust, too.
It is. It's known for durability, needs minimal maintenance, just cleaning like regular glass. Comes in different formats, too, laminated into glass. As a self-adhesive film you can add to existing windows.
Oh, so you can retrofit it?
Yep. Self-adhesive smart film is big for retrofitting. Ideal for those interior spaces needing instant privacy meeting rooms, patient areas, offices.
Okay, PDLC seems straightforward and effective. What about SPD, suspended particle devices? How's that different?
SPD is a different mechanism. Instead of liquid crystals, it uses microscopic light-absorbing particles.
Awesome.
Again, they're suspended in a film between glass layers.
Light absorbing. Okay, so how does that switch?
Default state, no electrical charge. The particles are randomly dispersed. They block and absorb light, making the glass dark or tinted, sort of opaque or translucent.
And with electricity.
Apply a charge, and the particles align, creating pathways for light to pass through, making the glass transparent or less tinted.
It'll look different from PDLC.
Yeah, it often has a noticeable bluish-black tint, even when clear. Response time is also rapid, transitions in seconds.
Faster or slower than PDLC?
A bit slower than PDLC's milliseconds, but still fast seconds. The key difference, though, is privacy and control. SPD offers, let's say, weak to moderate privacy, even when fully dark.
Okay, so not total blockout like PDLC.
Right. But its big advantage is that it offers instant and very precise variable control over the tint level. You can dial it in.
So it's dimmable, basically.
Exactly. Which makes it really well suited for applications where you want quick adjustments in light or glare, but maybe don't need total privacy. Think automotive sunroofs, windows, aircraft windows. It's excellent for glare control.
Got it. So PDLC for privacy, SPD for variable tint and glare. That leaves electrochromic or EC glass. How does that one fit in?
EC glass works differently again. It uses an electrochromic film and a small DC electric current. Applying that voltage causes ions, tiny charged particles, to move within special layers in the glass, often including materials like tungsten oxide.
And that movement changes the glass.
Yeah, it changes the reflective properties, making the glass darken or lighten to control sunlight and heat passing through.
Okay. How does it compare on speed and power?
Speed is its main drawback. It's much slower than PDLC or SPD. It can take seconds, sometimes even minutes, to fully transition between states.
Minutes, wow, okay.
But a key difference in power. EC glass is often bistable, meaning it holds its state clear or tinted without continuous power. It only needs a pulse of energy to make the change.
Ah, that sounds very energy efficient then, once it's set.
It is, for long-term states. Privacy-wise, though, even in its darkest state, maybe less than 3% light transmission, you can still often see through it somewhat. So, limited privacy.
So where is EC glass typically used?
Its real strength is in solar control and glare reduction for large exterior glass surfaces. Think building facades, big skylights, where that slow transition time isn't as critical, but controlling solar heat gain over the day is really important.
Makes sense. But are there any downsides? Apart from speed and limited privacy, what about cost?
That's a big one. EC tends to be significantly more expensive than PDLC or SPD.
Ah.
Yeah, the materials and the integration can be costly. Despite some impressive large-scale installations, reports indicate major producers have struggled with profitability. So its economic viability, widespread adoption, has faced some hurdles compared to, say, PDLC.
Okay, that clarifies the main active types. So we've got this amazing glass-changing buildings. But you mentioned it's part of a bigger picture, smart materials. And that connects to the second innovation, these bistable glass-coated microwires. Seems like a leap.
It might seem like a leap, but you're right. They both fall under this umbrella of smart materials, which are really just materials engineered to respond dynamically to their environment. They sense something and they react or change in a useful way.
Giving materials a kind of intelligence.
In a way, yeah, an engineered responsiveness.
What's next? What does the future look like for smart glass and maybe smart materials generally?
Well, one major development for smart glass actually connects back to that bistability idea from the microwires. People are working hard on bistable glass systems.
Like the electrochromic glass, holding its state without power.
Exactly. But potentially faster or with better properties. The goal is glass that holds its transparent or opaque state using zero continuous power. It would only need energy during the actual switch.
That would be a massive energy saving, especially for large buildings.
Huge. It could really unlock the next generation of energy-efficient smart facades, buildings that actively manage their energy use through their skin, integrated with IoT systems.
Beyond bistability, what else is cooking for smart glass?
Lots of ongoing research. People want even better clarity, lower power consumption still, more resistance to weather and UV for exterior use. We're also seeing exploration into flexible, switchable films.
Flexible, so you could curve it.
Yeah, imagine dynamic architectural shapes, not just flat panes. And glass that could maybe change colors dynamically or fine-tune transparency based on sunlight, occupancy, user preferences.
More intelligence baked in.
Definitely. And deeper, more seamless integration with smart home and building management systems, AI-driven climate control. It all becomes part of a connected ecosystem.
And the sustainability angle seems huge too.
Absolutely. Smart glass is really positioned to be a key player in green building, reducing reliance on mechanical blinds, optimizing daylight, cutting HVAC loads. It ticks a lot of sustainability boxes.
Okay, this all sounds amazing, but let's talk brass tacks. The cost. Is this stuff still prohibitively expensive? What's the economic reality?
It's definitely still a premium product compared to standard glass. The initial cost is higher. We mentioned some ballpark figures earlier. PDLC maybe $70 to $120 per square foot. EC maybe $130 to $180.
It's quite an investment up front.
It is, but the key is the long-term return on investment, the ROI. You get significant energy savings over time. You could potentially eliminate the cost and maintenance of blinds or curtains. You might gain more usable space near windows because glare and heat are controlled. And there's the aesthetic value.
So does it pay for itself? Is there a typical payback period?
For commercial spaces or healthcare, where energy use and functionality are critical, the analysis often shows a predictable ROI. For PDLC, it's often cited in the range of, say, 3 to 5 years. So the initial investment can be recouped reasonably quickly through operational savings and benefits.
Okay, that makes the economics much clearer. It's an investment, but one with a tangible return.
Exactly.
Right, so let's try and wrap up this deep dive. We've covered a lot, from glass that thinks, well, responds.
Yeah, responds dynamically.
Responds dynamically to give privacy or control light, all the way to these incredible tiny microwires that can sense stress inside solid steel contactlessly. It shows how materials themselves are becoming smarter, more efficient, really adaptable.
And understanding this isn't just about, geeking out on cool tech. It's really about seeing how science is actively reshaping our environments, making them more efficient, more comfortable, more sustainable, even and potentially better for our well-being.
Which brings us to a final thought to leave you with. We've seen how glass and tiny wires can be engineered to be so responsive. So think about this. What other things in our daily lives, things we think of as completely static and unchanging, could be transformed if we gave them these smart properties? How might that change the way we live, the way we work, how we interact with the world? And what new possibilities, or maybe even new challenges, could emerge from a future where more and more objects around us become dynamically responsive?